Howdy, this is Mr. Potter. What I want to do today is I want to take this merge sort that we came up with, and I want to make it reflect our fraction class. Remember that we wrote a fraction class. We've been adding to it as we've come across. Our fraction class actually allows us to compare two fractions using this method called compare to, which allows it to compare itself to another fraction. And we get a number that's less than 1, less than 0. I mean, if our fraction comes before this other fraction we're comparing ourselves to, we get a number that's greater than 0 if we have a fraction that we are bigger than this other fraction. And we get exactly 0 if the two fractions are equal. So what I've done is I've taken what we talked about before and I put it in a class called recursion, because we're going to add a couple of things to this over the next couple of lectures. So this is basically going to be a static recursion class that we're going to be calling upon static methods to manipulate our fractions. I've also taken the main that we had originally written, and I put it in this fraction recursion driver here. So what I've done here is, I've imported Java util arrays. I've created an array of fractions, and then inside this loop, I create a random numerator up to 20, a random denominator up to 20, making sure, of course, that it's not 0. And then I just create a new list, and this is the exact same code we had before. I'm just calling on the static method MergeSort in our class recursion. But this is not going to work, and the reason it's not going to work is because when we originally wrote our MergeSort, required integers arrays, and we have an array of fractions. And so there's a couple of things we have to be aware of in order to do this. Of course, first, the idea is our public face of this. We're going to have some array, but it's not going to be of type int. It's going to be of type fraction. And when we make a duplicate array, this duplicate array also needs to be of type fraction, and it needs to be the same length as list.length. So all I'm doing is I'm just making this, instead of an int array, a fraction array. And I want to pass both of these methods to our recursive MergeSort function. Remember that our recursive MergeSort function had a int array list and an int array temp. I want to change both of these to fractions, but I don't want to change this and this. Remember that start and end were actually indices of the array. They weren't fraction. They weren't integers to sort. They were telling us the start and the end index of the array that we're trying to sort. And in this method, we had our if statement, which is just comparing those indices, and we needed to find a midpoint and use the recursive merge sort and then the merge method. This was the hard part, and this is where we're actually going to have to do the most changes to. The obvious changes are instead of an array of ints, these need to be an array of fractions. But start and end again are indices. They're the places in our array. So we're not going to change those. Mid, head 1, head 2, and spot, these are also indices. And I'm checking to see if the indices are within a certain range. In other words, this is in the first half of the list, was this in the second half of the list. This is the big thing we need to change. I wanted to know if what was in the list first comes before what was in the list second. And we can't use less than when we're dealing with objects. This is where we have to use that dot compared to. And I'm doing compared to with list subhead 2. And I need to make sure that this value, because I wanted list subhead 1 to come before list.head 2, I want to make sure that this value ends up being less than 0. So the first list has the smallest element. If I compare the element in the first list, if it compares itself to the element in the second list, we get a number that's less than 0. And if that's true, then we want to do this copying over. But temp is an array and list is an array, both an array of fractions, so we're cool. Spot and head 1, they're incrementing, but they're the indices of the array. They're not the actual integers we were sorting. And the else takes care of this other swap down here. And when I'm in this while loop, remember that head 1 was an index of the array. It started at the starting index. And mid was an index of the array as well. That was originally start plus head divided by 2. So I don't want to change any of these. And then this is just a simple copying. This is exactly the same thing, but it's doing it for the end of the list. So this method is fine. And then this was just copying elements from our temporary list back to our original list. Let me copy this, make sure this works fine. That like seems to work okay. I'm going to go ahead and compile our fraction recursion driver. See if there are any issues there. No problems there. We had our fraction class, and I went ahead and copied it, make sure I have our class files all in the same folder. No issues there. So I'm going to run this. Remember what this did is it created an array of 100 fractions. It printed out the original list of fractions. Remember that we had a two-string method that allowed us to print out fractions. Where was our two-string method? Up here. It prints numerator plus a division vinculum, and then the denominator. And then we're going to sort them, and then we're going to use the arrays.toString method to print it again. So we're going to run this. And so I see our array. Here's 12 over 6, 6 over 9, 1 over 3, 13 over 10, 13 over 9, 7 over 14. These aren't reducing, and that's fine. But then we sort it. We have 0 over 8, 1 over 19, 1 over 19, 1 over 17, 1 over 15, a whole bunch of monic fractions here. 2 over 14, which is 1/7, 3 over 18, which is 1/6, then 1/5. Then I've got 2 eighths and 1/4, and the order here really doesn't matter because I only swapped, or I only put it in position if it actually came before, not if it was equal to or greater than. So our merge sort works. So then what I want to do now is I want to talk about another recursive method that we're going to write here. And this is going to be a binary search. So the whole idea in a binary search is that I'm going to take an entire list, but I'm going to start searching in the middle of the list. And because I am working with a sorted list, remember that binary search requires a sorted list. I know whether or not I need to search in the first half of the list, or if I need to search in the back half of the list. And of course, the only problem I have is that if the index of the first half of the, and if the index to the front of the list and the index to the back of the list end up crossing at any point, then I know that my element doesn't show up. So what we're looking at here is, let's go ahead and talk this out. We're going to have a public static int binary search, and I'm going to pass it a parameter, a fraction array, which I'm going to call list, and a fraction, which I'm going to call target. And what we're going to do is we're going to look for this in our target, but I really need to have some notion of where the starting point is and where the ending point is, because I only want to search from the start to the end, and we're going to take care of this recursively. So the idea here is that if start ever ends up being greater than end, then I want to return -1. That's our base case. In other words, the whole idea of the searching, I'm either going to find what I'm looking for, or I'm going to find evidence that it's not there. This is the evidence that it's not there. So base case not found. And if list sub, actually I want to do one other thing first. I want to say mid, this is going to be my middle index, is going to get start plus end divided by 2. This is the place to look and to divide the list up if it's not here. But again, I need to check to see if it actually is here. So if list sub mid, don't do that, is equal to the target. But remember that we can't use equals because we're dealing with objects. I physically need to use the dot equals method, and I need to see if it's equal to the target. And if that's true, then I want to return mid. So this is the base case. We found it. So now I need to go to my recursive case. So in other words, if we didn't find it, I need to know if it's in the first half of the list or if it's in the last half of the list. So if list.mid, list submid, and I want to know how it compares to target. So dot compare to target. And if I get a number that's less than 0, this means that the element that we're looking at comes before target. So we need to search the back half. So I'm going to return the result of binary search for my list, for my target, but not starting at start, starting at mid plus 1 and going to end. So this is the recursion. The idea is that, well, if it's not in the middle part of the list, I need to search one of the other halves of the list. So I'm going to call on binary search again. If I've not found it, if I know it, if my start and my end are still good, if my midpoint doesn't have it, and if comparing the midpoint to my target, my midpoint comes before my target, so here I had to search the front of the list. Else, and again, I'm going to put the else in comments because I really don't need it. Because I've been using return statements, if I'm at this point of the program, this is my only option. I need to return the result of binary search for the front of the list. So list, target, start, and mid minus 1. So this is another recursion call. Now remember, this is the actual recursion method that does everything, but we really want to have a public face and a private face. So this is going to be our private helper function. Our recursion is. And we're going to create a public static int binary search, which is going to take a fraction list, fraction array list, and a fraction target. Because when the user wants to search something, they're not going to care what the start and ending list is. They're going to say, here is my list. Find it, or tell me that it doesn't happen. So I want to return the result of binary search for the overloaded version, for the version that has a list and a target and a beginning, which I want to start at 0, and the end, which is going to be list.length. And I'm just going to return the result of whatever the binary search call is. So just a real quick recap of what we're doing. I've got this private static int binary search, and it's got 4 parameters. I've got the list I'm trying to search. I've got the target that I'm trying to find. I've got the start and ending index values that I'm searching. So I'm going to be searching from here to here. Maybe it's the entire list like it was at the very first call. But maybe I just want to search between elements 4 and 7. And so the first thing I'm going to check to see, do I really have valid starts and ends? Because keep in mind, if I don't find my item, I'm going to be searching at mid plus 1 to end. Maybe I'm going to run into a situation where mid plus 1 and end are the same value. I might run into the situation where mid plus 1 and end are out of order. That mid plus 1 actually comes after end. And if I reach that situation, or similarly, if mid minus 1 ends up being before start, then what I'm looking for isn't in the list, and I just want to return -1. And we've talked before about how these search methods will often return a negative value to indicate an error, but still allow the program to run without tossing an exception. If I get past that hurdle, then I'm going to check the middle point, the start plus end divided by 2. And it's either going to be there, or it's going to come in the front of the list, which I get by using the compare to and checking to see if it's less than 0. That actually checks the back of the list, not the front of the list. Because if what I'm searching at, what I'm looking at in the middle, comes before my target needs to come after the middle. So it needs to come at the end of the list. Else, then I check the front half of the list. So this compiled without any major issues. Okay, it didn't. Let's fix that real quick. Oh, extra brace. I apologize for that. And it's thinking. And then I'm going to take my fraction driver. Remember that it has to be sorted. So I'm going to say int spot is going to get recursion dot binary search. And I'm going to pass the list, and I'm going to get a new fraction with 1, 2. In other words, I want to search my list for 1/2 and see if 1/2 shows up in the list. Now I've tried to make this 20 and this 20 so that 1/2 has a pretty good chance of being in the list, but these are random. So I could run into this situation where I actually get a -1. And I want to system.out.println, and I want to say that 1/2 shows up in position spot. So we're going to go ahead and run that and see what happens. So I get my original list. Here's my original list pre-sorted. And that bodes well. I see the 8/16. So I know 1/2 is in my list. And then here's my sorted list. I see a whole bunch of zeros and other things. And remember, I'm looking for 1/2. So there's 1, excuse me, that's position 0, 1, 2, 3, it's position 4, 5, 6, 7, 8, 9, is that 2 15s, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Now, keep in mind that it's finding the first place it's found in the binary search. It's not necessarily finding the first place in the list. Because here I had 8/16, here I had 3/6, here I had 5/10, here I had 9/18. These are all equal to 1/2. But keep in mind that I have 100 elements in my list, which means I'm doing 0 plus 99 divided by 2, which is 49. And 1/2 must come before that midpoint, so we search the front half of the list. 0 plus 49 divided by 2 gives us 24, and this was the first one that it found. So we've got this recursion class that we're putting our methods in. And I think it's important to have these public faces that the user can use very straightforward. But then if we're going to use the recursion, we need to pass along some extra information, some extra parameters. And so these really need to be private. So in our next video, we're going to handle a more advanced sort, something called Quicksort. But it also is a recursive sort, and so we're going to put it in the same vein. We're going to be putting it in here with using our fraction class, because I really think that dealing with this fraction class is kind of a year-long case study. The idea of taking a class and really evolving with it is important in understanding computer science. So once again, this is Mr. Potter. Thank you for watching. Have a great day.